I will be talking about, in general, energy to start with, and then what happens in buildings in terms of heat transfer using 3 principles. And we'll try to connect all the time with each slide with some what happens in buildings with some examples, maybe impromptu examples, and also we'll try to help you understand how do we really assess the heat transfer, or how do we really measure the heat transfer. One or two requests. The abridged version of a presentation would be available to you. So you may not concentrate in copying anything which is there. So that's number one, because I generally feel that if you are just taking it down, there would be a data loss. So what you are taking it down, and then later on when you read, it may not really make the same sense as it is going to make here. So just concentrate on what I'm saying. If you have any question, just raise that question right away. If it is a really pertinent question in helping us in the presentation, I will deal with it right away. Otherwise, we'll park it aside and we can take it later on. But don't hold any question to yourself for a longer time. Just ask right away. Okay? So, what are we trying to understand, or what are you trying to study is, and as you know, that we need to have a certain kind of a boundary condition under, or certain kind of framework under which we understand. And when it comes to study or quantifying energy, we try to find some boundary conditions under which we work. So, for example, right now, and for the matter of the BEEP camp, the building is a sort of a boundary. We are not going to talk too much about what happens outside building and what happens in the region and urban area and so on and so forth. So I would say building envelope is sort of our boundary. Whatever is getting affected or whatever things which affects it, we will be discussing that. Whatever is getting generated from the building in terms of loads, we also will deal with it. So that's what brief about the system boundary as a part of the building, the mass or energy which is leaving the system, and mass of the energy which is impacting the system is what we will be focusing most of the time, at least in these 2 days, and then later on as well. As we know that it is, what is it? It's basically a potential to do or potential to carry out work. So if some mass is here, needs to be transported to this place, what you require is a force. And Newton and joules are sort of units which we use. All of you would have studied this in your 8th, 9th, 10th standard. I'm just making it sure that there is something like Newton per meter square, or there is something like meter per second square, and so on and so forth. Various kind of energy or forms of energy, microscopic and macroscopic. When it comes to buildings, we generally, or not generally, when it comes to buildings, our focus is microscopic, which means that it is a sensible and latent load, sensible and latent energy. And these two are, in a manner, the focus of all building energy efficiency. We do not talk about chemical or atomic bonds, or atomic energy with the bonds with the nucleus, and so on and so forth. So when it comes to buildings, we try to look at the sensible energy and latent energy. And sometimes we turn this into sensible loads and latent loads. And later on, Prashant and Pierre will talk about how do we really manage these two things separately. But sensible load is basically transitional, rotational, or vibrational. Latent load is when we are in the change of phase conditions. And we'll try to explain that a little bit more. Internal energy is a sum of all microscopic energy, sensible, latent, and chemical and nuclear. Just refreshing what happens when you have water at certain, let's say 25 degrees centigrade, you try to warm it up, what is getting added is a sensible energy. And then at some point in time, vapor and liquid both will exist, and the temperature will not really change. That's where we talk about latent, and then onwards again, it's all vapor. So in terms of a temperature rise, there is no temperature rise when you're in a latent phase, but there would be a change in a energy. So when material is during the change, or which is changing the phase, it does absorb or give away thermal energy without changing the temperature. There are new materials which are getting into market called phase change materials, and they actually use this principle to get you either reduction in energy or give you a higher degree of comfort, or extended period of time it can give you comfort. It does not change its temperature, but it does change its phase to get you certain kind of output. We will talk about the phase change material when we'll go to a lab day after. But that's where the internal energy really helps us to understand. So repeating that, sensible energy, which is molecular motions, and latent energy, needed to affect the change of phase. Again, a repetition, the way energy flows from higher temperature to higher internal energy. So temperature indicates the level of internal energy a mass can have. A unit, and quite some time, if you refer some of the literature, it does talk about Fahrenheit or a Kelvin as a unit, and you should not really get confused with that. It's simple is the difference between Celsius and Kelvin is just about 273 degrees here. So if you have, if you are referring to Kelvin, where that means that there is, at that point, at that temperature, there is no thermal internal energy, which is 273 degrees minus 73 degrees centigrade, which we define it as a Kelvin, and 0 degrees centigrade, that means plus 273 degree Kelvin. So if we have a water at about 25 degrees centigrade, and if we put a hot brick which is about 80 degrees centigrade, you can guess what will happen, right? What will happen? Sorry? What will happen to brick? It will cool down. What will happen to water? Okay. How long will it take? Sorry? Yes, that's fair. So basically, 80 degree will try to become 25 degree, and 25 degree will try to become 80 degree, and wherever this gets settled down, that will be the sort of point. How long will it take? So if I have a Jaisalmer Haveli, if I have a 42 degrees centigrade outside, my windows are closed. There is some degree temperature inside we don't know how much. And then in the evening, when temperature drops, and as you know, in hot and dry climate, the temperature variation between day and night could be very, very high. Temperature will drop to about, let's say, 28 degree. You will open window, air will flow in, inside a temperature which has been, whatever was there, will try to get to closer to 28 degree, right? Because the air which is outside is flowing inside. Versus a basement of a Jaisalmer Haveli where you do not have any windows or no means to change the air. If outdoor temperature, this is basement, so outside soil temperature, let's say it goes up to about 32 degree and inside is 25 degree, how long will it take for this 25 degree to go up to 32 degree? Why I'm saying 32 degree? Because outside is a soil and it's a huge mass. With that small air, cannot change the temperature of the soil which is outside. So obviously the air temperature, even if it loses the heat or loses the cool, the temperature will go up, right? How long will it take? Depends upon thermal mass. Do you really need to have numbers to state this? I was hearing there are some people who wants to really understand building physics, wants to do simulation tools. Yes, all those are fine. All those they help us to pinpoint or really find how much to do. But when you come across this kind of questions, you don't need to think much. It should be there right away in your mind, and the answer will be, it will take forever. Because the 45 degree or the 80 degree will start going down, it will become 75, 70, 65, and then it will slow down, right? The flow will slow down, this will go up, it will take ever. So in Jaisalmer, if you don't have any windows in the basement of Jaisalmer Haveli, and if outdoor soil temperature needs to get, it will take forever. It will slow down over a period of time, right? What you can achieve in first 24 hours, next 24 hours, you might not be able to achieve half of it. And then it will really slow down. And this is where we need to understand that when we talk about heat transfer, we are not just talking about one way of heat transfer, not the conduction, but the way we understand that, the moment you open a window, something will flow in. So then convection will start getting into the picture. So keep thinking that at every time, all these three, conduction, convection, radiation, when it comes to a building, when it comes to a human being, we have one more ways of losing or gaining heat, or rather losing the heat, which is evaporation. We perspire, right? And we'll talk about that when it comes to a thermal comfort lecture. The point I'm trying to make here is that when is also important. That you may calculate, in the afternoon we have a tutorial, you may calculate point in time, but the way EPI gets measured over a period of time, heat transfer also needs to be measured over a period of time. Why EPI? Why do we have this meter square per year? It's like profit and loss bank account of a trader, right? In vacation time, this canteen guy does not make any money. But when we have exam times and submission time, his profit goes up. So basically, at the end of year, he looks at whether he has made a profit or he has made a loss. So energy is also, it's not, you just need to look at one point in time, but it's over a period of time, because outdoor is dynamic, indoor is dynamic. Right? Summer, winter, season, and vacation period, non-vacation period, all that is dynamic. So all what we are trying to look at here, right now, definitely at the point in time, but you must have that all this is going to happen in sync with outside and inside. It will keep varying all the time. Okay? And that's where the heat flow rate, Q, comes into the picture. The total flow in a unit time through a defined area of a body or a surface. So how much will it transfer from 1 square meter of X amount of wall? How long will it take? So that's where the heat flow rate becomes important, and we measure that in a watt or kilowatt or joules per second. Same unit as what we use in a power. Heat flow rate density, which is watt per meter square. How many watt of energy will get transferred from one side to other side if you have 1 square meter of an area, or watt or kilowatt. So the second thing, which is the capacity of any mass to retain the heat or energy. We call it a specific heat. And as you can see here, that various materials have a various capacity to retain heat or to retain energy. For not getting too much into the complexity of what is energy and what is heat, and there is a difference between energy and heat, for a while we will use that sort of interchangeably. We said heat and energy, and sometimes electricity is also energy kind of stuff. But it's, for a while it's fine the way we are using. So, you know, amount of a heat capacity various material has. Some really have very, very high, as you can see, water. Really retain heat a lot versus a brick, not as much as, right? So when Professor Lal was talking about, very briefly he mentioned that the Irad building, or SM Sehgal now? SM? No. Sehgal Foundation building is where they use water in the roof or ceilings to cool down the space, radiant cooling. So radiant is a principle which they use, but material they use which can really absorb or release heat much more. See, this is exactly amount of heat it can absorb is much higher. So amount, 1 liter of water versus 1 liter of air, who can retain or who can absorb more? Obviously the water, right? 4 times more. And hence, in that building, somebody is using this principle. No, that somebody is using this material and a principle of radiation to absorb heat or to reject the heat from the building, right? So that's what the heat capacity, all of this, I'm again sort of not really getting into the nuts and bolts of it, but yes, amount of, let's say 1 kilogram of water, which is about 25 degrees centigrade. And if you have to rise its temperature from 25 to 26, you probably need to give about 4,000 joules of energy. Then its temperature will rise. This is how we interpret, okay? And then there's a MCP delta T. This is all the time we keep using this equation. Is that how much will it take, and sort of at what temperature difference you store heat or you reject the heat. The change in internal energy depends upon amount of heat you add to the system and amount of energy you need to work, right? So delta U, which is U is a change in internal energy, is equivalent to amount of heat you add to the system and a work it carries out. Okay, delta U equal to Q minus W. Second law is that spontaneous direction of heat flow between two bodies would be from hot to cold. And the more the difference, more the flow. Less the difference, less the flow. Right? It's very similar to our water tanks. If you leave the water tanks and on its naturally, if water has to flow, obviously it will flow very quickly and then slowly it will come to us. So basically heat moves from higher temperature to lower temperature. All these which we have, what I'm showing you, we have gone through this. And it might be there somewhere in your mind. I'm just refreshing it. Nothing else what I am adding to your knowledge. And then we have these three principles, which is conduction, convection, and radiation. Right? Conduction is a heat transfer in a stationary medium without bulk motion. That means nothing is moving in terms of a fluid. And the way we transfer the heat is through the stationary medium. And this is where walls and roof, and predominantly wall, is where the conduction takes place. And that's where wall U value becomes important for us when you try to look at the heat transfer in wall. So, and many times we need to really convince people that what is conduction, and the best thing which I have understood is that People always get confused that, no, but if there's a lot of solar radiation is getting onto my wall, but if I shade the wall, it will not be, the surface temperature will not go up. You say that's true. But then you are talking about a radiation impact on the wall, right? And the another way of looking at it is that, raat mein garmi lagti hai ki nahi lagti? That means there is no radiation, but still, if the outdoor temperature is 35 degree and you want to have 27 degree inside, you need to cool down some ways. That means when you look at the conduction, you are not looking at air, you're not looking at sun, just looking at a temperature variation, right? When it's to convection, obviously you need to have a fluid which can transfer the heat. That fluid could be air, the fluid could be something else. And that's where the convection helps us to gain or reject the heat. When it's come to radiation, it's basically is electromagnetic waves with or without medium. So sun is so far, we still get a heat, primarily because of the electromagnetic waves, and you don't require any medium in between, right? And still it transfers the heat to us. That's the power of radiation. And the same, so that means that one of the most effective way to reject or gain heat is through radiation, because there is no agent in between, right? No one is eating up heat. If you have someone in between, obviously that in between agent will eat up something. When it comes to radiation, there is no in between, right? And hence the SM Sahgal Foundation, which is using the radiant system, electromagnetic waves helping you to achieve comfort. The air which is there inside is not eating up anything. Right? Getting my point? Okay, thanks. So you have let's say a metal bar, and try to warm the metal bar from one point, from hot side to cold side after sometimes both sides. And this is where a conduction heat transfer. You have a mass which is sort of absorbing and which is transferring the heat. Convection is basically a fluid which helps you to gain or reject heat. That fluid could be used in a natural way or sometimes could be forced. So natural convection happens when you have a temperature variation, right? And sometimes you also put a forced convection. Professor Lal was talking about Jula yesterday. It was a forced convection, right? But sitting next to the Jharokha or open window, probably you are trying to rely on a natural convection. Okay, when the fan is a forced convection versus you can have a natural convection if you're just sitting below the tree without radiation. Now this is where the natural convection also sometimes gets affected by gravity. And in next lecture we'll see how the gravity also impacts the cavity walls. For example, all of you are aware about cavity walls. You have a brick, then you have a cavity, and that's where you are using that low conductive material like air as an insulating layer, right? But then if that air starts getting certain kind of convective current, it will start transferring the heat, right? So it may not work as a still air. The moment it starts getting some kind of convection inside, it will start gaining or losing heat. So if you have a hot side here, and if you have air, and if you have a cold side here, and some kind of so density variation, air will start moving because the surface here is hot, surface here is cold, and that air needs to achieve a same temperature. So this much amount of air if it is at lower temperature, will rise to a certain temperature, and that's where it starts conducting the heat. So air will become a medium to transfer from here to here. Yes? So hot wall emits more than what receives, so it cools down, and cool air or cool wall will receive more than what it can emit, so it will become hotter. But they are not touched with each other. They are not, the air is sort of medium which is transferring that heat. That's where the convection comes into the picture. Fair? Okay. As I was mentioning, sun is so far, it still gives us a heat relying on electromagnetic waves. There's no medium in between. So when you have, when you see a fire placed like that, this guy is getting warmth. Which principle acts there? Which principle is working there? Can somebody tell you? Obviously the slides talks about radiation, so you said radiation, but something else is also happening. What is happening? Where? Where is convection? Where does this warm air goes? That's correct. So there is a chimney here. So there, the warm air goes up, so that's convection taking place, but this guy is getting comfort because of the radiation, and not only, or rather I would say the convective portion would be much lesser for him to become comfortable. Right? He is getting comfort primarily because of the, and whoever has made this, he's a pretty sensible guy. He has not made this guy wearing a pullover. I have seen number of examples. Person is sitting next to the chimney or sitting next to the stove or sitting next to the radiator wearing a woolen. Do you know what will happen? Do you know what would be the density or what would be the thermal conductivity of our sweaters? And will it actually help you to get that? Yes or no? This is complex problem. I'm trying to confuse you. Just imagine if this guy is wearing a pullovers. Pullovers have a low conductivity, right? That it does not allow anything to go from inside to outside and outside to inside. But still, this guy will wear it next to the chimney, or even if it is standing on the sun roof or in the sun spaces, he will still wear it. Will it matter? Yes or no? Will it help? Will it not help?
Try to retain the thermal heat that your body already received.
That's correct.
Thermal air will try to retain it.
Right.
Because you're receiving
Fair. That's understood. I'll repeat that for the rest of the class. But second, will he get affected by the fire? Sorry? Okay. Okay. So this is some, sorry? Okay. That's a mistake I was looking for. The thermal wear is actually not going to reject anything which is coming through radiation. Right? It will reject if it is a conduction or convection. So there are two things which is happening. One is that person's own body heat does not go out because he is wearing a low conductive material on top of his body. But when he is relying on a radiative heat transfer, he can still take advantage of that, because radiation does pass through. Now then what he was talking about, the black body and stuff like that, we'll come to that in a while. But if you are wearing something which can reject the radiation, then that the fireplace will not help you. But what you're wearing is, it can still accept. So the other way of looking at it is, let's say if we get okay, anyway, I'll stop here because that we will take it when we'll talk about thermal comfort. Okay, Let's focus on heat transfer right now. Now, when it comes to building, all of you know that we have long wave radiation getting on a building. Part of that will get through the conduction, part of that will get rejected back, depending upon what's the surface, what's the characteristics of surface you have on the roof. If you have window, direct solar radiation will get in the short waves, right? Convection, where you rely, and we call it a ventilation, convection and ventilation has direct correlation. Then you have internal gains as well, right? You have either lights, or you have a projector, you have a computer. All of you are emitting heat, and then through conduction as well. Do you know how much heat are you generating right now? So if I imagine that, or if I have a power of any animation cartoon character, and if I ask this guy to come here, and if I said shh, and if I reduce him to about 4 inches or so, I'll not be able to do handshake with him. He'll be so hot. He's producing probably about 60 watts of energy right now. But I can do handshake with him because it has been dispersed over the surface. If we reduce him, it'll be like incandescent bulb, right? So, sorry?
It's like EPI,
Let's not go there. So, basically what will happen is that amount of heat which he can dissipate through a 5 foot 9 inch or 6 feet of body, he will be doing that with 4 inch by 4 inch cuboid, and then hence the surface temperature will go up. Right? So that's the amount of heat we are also generating inside. So that's the internal gains are. I need to do a little quickly. So daytime heat transfer, you do have a higher temperature. So through conduction something takes place, but then you have a presence of sun, which is not there in the night. You still have a conduction. If your temperature drops down, you will have some kind of convection taking place. But then, whatever has been absorbed during the day, if the surface property allows, you might reject that back into the atmosphere. So heat conducted through the roof during the daytime may get emitted back, depending upon what surface treatment you have. Okay? Now, a little bit about materials and construction. And the way I try to explain people is that when you have a walling material, you have two sorts of ways by which you need to, okay, just let me, if you feel a little drowsy, if you feel that you're finding difficulty in concentrating, please step out, wash your face, take a fresh air outside, come back. And you don't need permission for that. Just step out, okay? I'm seeing one or two guys are finding a bit of difficulty in concentrating. And let me tell you, I am not a culprit of that. All of you are producing carbon dioxide, and carbon dioxide level is going up, and that is affecting you, not me. I'm not that boring. So, when it comes to walling materials, masonry units, sheets and boards is generally the way we try to, and my lecture is going to focus on walling materials and roofing materials, which are sheets and units, not really in situ material, except for one example which I said in situ. In situ, as you know, that you cast on site. And when it comes to fenestration or windows, I'll try to deal with the window frames, glass, and overhangs. We will not talk about internal walls, because we believe that it is a focus, it should be a focus if it is a building which having a various kind of spaces, some of them air conditioned, some of them not air conditioned. Otherwise, we are assuming that this particular wall is sort of adiabatic, there is no heat transfer taking place because amount of, temperature here and temperature other side of the wall, same, and hence for simplicity, the lecture is going to focus on external walls. We are not going to talk about skylights and doors. We will just focus on windows, and we'll talk about roofs. We will not talk about floors, not talk about foundations. So these are the things which matters when it comes to sensible load, when it comes to envelope performance. And in terms of how do you really evaluate them, what kind of units you come across when you are looking at walls or fenestrations and roofs and so on. So in a manner, it's sort of, and if you start looking at the units, you will realize that who gets affected by conduction, who gets affected by conduction and convection, and who gets affected by conduction, convection, and radiation, all three together, right? So let's look at the walls. The units which we use, or rather the parameter which impacts is the conductivity, how much heat transfer takes place, or how much rejection of heat. Thermal mass, specific heat of that, whether it's a brick or it is a concrete, who can store more heat? Mud, who can store more heat? And a diffusivity of it. When it comes to a fenestration, as you can see, you have a R or U value. Sorry, this should be changed. So do you have a solar heat gain coefficient? No, it's correct. And you have a visual light transmittance. So when you're evaluating a wall, you're just looking at a U value and at the most specific heat, but when you're looking at fenestration, you are looking at three things together. And when you're looking at roof, again, U and R value, and then you are also looking at solar reflectance. Although generally, theoretically, there should not be any difference between walls and roofs, because both are external, just a geometry-wise or the placement-wise, something which is horizontal and something which is vertical, everything gets affected. Everything does affect wall as much as roof. But we talk about roof a little bit more in detail when it comes to solar reflectance, because we try to understand, yes, the performance of the roof and what's its ability to reflect the solar radiation back into the atmosphere. And we do not talk about the same parameter of the wall, because the moment you start talking about same parameter wall, your eye or your view exposure comes into the picture, and we really don't want our eyes to get affected by that solar radiation. Hence, we don't really talk about that. So if you are a pilot, you might need to use ribbon aviators all the time if you do not want to get affected by that radiation. Otherwise, we're fine with this. The impact is more on the cataract. So if you are exposed to more solar radiation, you will develop a cataract. Cataract is nothing but some kind of protein on eye lens which gets accumulated, and you lose your sight for short term till you get operated. So when it comes to roof, we do talk about U value and solar reflectance. Material that restricts the heat transfer, the transfer of the heat in buildings, material that restrict the heat transfer better than structural materials. Better than structural materials, it is important to state this, because anyway we are having a load-bearing wall, and anyway we are having a frame structure, what can you do or what you need to do beyond that is where generally focus is. It's where when you talk about heat transfer, you talk about your starting point is anyway you have a wall, and what can you do beyond that, or what can you do along with it. Okay? So you have a thermal insulation which reduces the heat transfer and improves the comfort. In warm and hot climate, it should be used along with the solar protection. We'll talk about that in a while. And thermal inertia should be considered while using insulation. Now, this thermal inertia or a specific heat, the way I explain that is a raincoat versus Kumbal. Okay? For a while, just imagine or just put this in your mind that insulation is like raincoat. It simply rejects. Versus if you start using Kumbal in a monsoon, it will take a while before your skin experiences water. And it will take a while. This while depends upon what is the capacity of Kumbal to absorb water. And that is where the thermal mass comes in. So thermal mass is like your Kumbal, right, or Rajai, and insulation is like your raincoat, which rejects right away. Okay, it doesn't allow it. It does absorb a little bit, but basically for heat, it basically rejects the heat. And we need to somehow balance between these two. There is no silver bullet, insulation laga doge khatam ho jayega, then you are probably going to make a building which will function well if it's completely air conditioned building. And towards the end of this the lecture, I'll talk about how that is going to happen. But point I'm trying to make here is that our focus is also should be how are you going to operate your building. The construction and material selection is fully dependent upon how are you going to use your building. If I just imagine, if I insulate myself heavily, I will not allow any heat transfer through the conduction because my walls and roofs and floors are heavily insulated. But then every day morning I come and open windows, how that insulation going to help me? Right? My convection is going to, or impact of convection is going to override all that what I have done. So operation of the building also, when I say operation, it's not a use. It's not like office or school. But whether it is naturally ventilated or mixed mode or air conditioned building, how are you going to operate your building also comes in the picture. And selection of construction and material and construction is based on that. Why am I distinguishing between material and construction? Because you have a brick. A brick can give you a Flemish bond and English bond, but brick also can give you a red trap bond. So brick is a material, but construction varies when you have a Flemish and English bond versus red trap bond versus cavity. Hence, material and construction should be seen little separately in your mind. Okay? What should we do to reduce heat transfer? Yeah, conduction probably will move forward. And one way is to lock the air. What do we do when we put a fresh cut fruits into Tupperware or similar kind of, we try to lock the air. There will not be any air change. And then we try to retain the freshness of food up to a certain extent. Because radiation is also getting in many other things, and also the amount of air it has is also very limited, the amount of mass it has. But what we try to do is we try to lock the air, and air being a low conductive material, we try to take advantage of that and said, okay, can we have an insulating property? Right? So conductivity, just sort of going back, it's sort of amount of area you have, amount of thickness, and amount of heat which you transfer from one side to other side. And most importantly, in a homogeneous manner, homogeneous layer. We do look at the conductivity in a homogeneous manner, but when you are looking at a total heat transfer through the cavity as well, we start looking at U value straight away and not look at the K value. You don't look at the conductivity, because if you have a brick, conductivity is different, air conductivity is different, brick conductivity is different. So instead of looking at 3 layers of conductivity and try to juggle around, we always try to look at what is the total overall heat transfer, which is a U value, right? But when it is a single non-homogeneous or rather homogeneous cross section, we try to look at the conductivity to start with. And as you can see, huge range of conductivities, from aluminum to water to expanded polystyrene. Amount of heat gets transferred through that, huge variation, right? Some of them, and most of them we use in a buildings. And as you can see, from 1 to probably 10,000 is a sort of range. So if air is 1, just imagine if this is, where is air? So let's say air is somewhere at 1, 0.0002 square meter of aluminum, that is 2 square centimeter of aluminum, is equal to 1 square meter of insulation. And keep this in mind. When I talk about thermal bridge and thermal breaks, this will come into the picture. Okay? So there is something called thermal break, thermal bridge. And if you go one of the best way to learn heat transfer and apply that in building is to spend 1 year in a kitchen. And just, you may not cook, just keep observing it, right? So let's say if you have if you have to make a milk with the Bonvita and sugar, and you need to stir in between, you don't keep the chammach. You always take the chammach out. Why? Because you know that chammach is going to touch the bottom of the vessel, and a conduction will take place, and then later, next time when you want to touch the spoon, you will not be able to do that. What is it? It is thermal bridging, right? Rest of the milk it could be a low conducting material, but the spoon and that small tip which is touching the bottom of the vessel is bridging, and through conduction, more heat can get transferred. And now if you understand that 0.0002 square or 2 square centimeter of aluminum can transfer same amount of heat 1 square meter of insulation, right? So thermal break and thermal bridge is sort of opposite. When you have a low conductive material in between, we call it a thermal bridge or thermal break. When you don't have, it is thermal bridge. So if I have a wall, if I have a floor, and if I have a wall, this floor, just imagine this is balcony floor, and this is my bedroom. I have put in insulation either inside or outside, is different case, but let's say I have put in insulation here. But this slab, which is in a contact with outdoor, through conduction, it is still going to transfer some heat, right? And this is thermal bridge, okay? So this is what happens when you have a thermal bridging, but then you also need to take care that you may not, you do something like that, and you try to avoid the bridging, right? So this is where construction technique comes in, the detailing comes in the picture. Look at this picture. It's a thermal imaging of insulation. Insulation is fixed with sheet metal screws, and look at the amount of heat transfer takes place. That chotu will really spoil an effect of entire insulation. That means you need to do something so that that screw has a PVC sleeve inside. First the PVC sleeve will go, and then the fastener will go and will create a certain kind of thermal break to get the maximum advantage of insulation, right? So locking air also can happen in 2 ways. On left hand side, and these are the images which I have taken from Professor Roulet, who used to help us in an earlier part of the B program and has taught us quite a few things. And he has acquired this image on electron microscopes. Some of the organic fiber, what it does is it just reduces the flow of air. They create a certain kind of obstructions so that air does not move quickly. And then it's like Kumbal, right? And then they create an insulating impact or insulating effect. Versus someone are simply locking the air. And then there are two kind of sort of insulations which we get. What we are doing here, we are locking the air. What people do when they put the kuludi on top, they are locking the air. Mineral fibers, they don't really lock the air, but they reduces the flow. And pros and cons of various insulating materials, some of them are very good, some of them are not. When it comes to moisture, when they come in contact with moisture, obviously their performance drops drastically because they become wet. And the water impacts the conductivity of the material as well. Just looking at okay. So one set of materials are mineral fiber, and rock wool is one of the artificial. So basically, it's a artificial lava and basalt, and then heat it up to a certain extent and makes fibrous material. They generally get coated with resin, and so that their performance and their life increases over a period of time. They do get pressed with a certain kind of aluminum foil to keep them in a certain shape. Generally, they are compressible materials. They are not uncompressible. They are not rigid material. Hemp fiber and wool is hemp is also very widely used in European countries. Then we have a very advanced material like foam glass. They are rigid. They have very high compressive strength. So when you have to make a certain kind of floors, which is going to take a lot of load, and still you need insulation, you can go for material like this, or you have the perlite, which is generally been used on the rooftops. Now I have a question for you. We were talking about something like this, okay? And now we know that we have these materials. If I have to cover this space with the insulation, and assuming that this is 100% 24/7 air conditioned space, we are not going to open windows. Where will you put your insulation? Okay, so roof, you will put, so outside roof or inside roof? Outside roof, okay. And you are assuming that roof is made out of GI sheet and some plywood just to see so that it looks better. And you will put insulation outside, okay? Fine. What about walls? Are you going to put insulation on walls? Should you? Or it's not required? It's required, okay? Why it is required? So through the conduction, there would be heat transfer, and hence we will require some kind of insulation, whether inside or outside, that we can talk about. Anything else, anywhere else? Okay, so wherever there is external heat transfer taking place, first of all, you will identify those elements and you will place insulation. Now, place inside, outside, that's a second question. Okay. They are roof and walls. Floor? Is it external? Ground floor. Okay. Fair. So we will have something on the floor, we have a wall, and we'll have roof. Now let's talk about where will you put it. You want to retain certain amount of environmental condition inside. Outside is varying. When I say air-conditioned building, it's easier because you know that every time I need to maintain 27 degree plus minus 1. That's it. So if outside is 45, outside heat should not get in. If outside is 12, inside should not lose. Right? So where will you put insulation? You are not asking where is this building. Are we assuming that this building is in Ahmedabad? Right? So selection of material, selection of construction, based on use, and what I forgot is based on where are you building it. Climate also will make one of the parameter on which we need to decide. So this foam glass, gets used when you have to take a lot of load on the floor. Generally, it's expensive material. We don't really use it on floor, on the roofs, because there are other material available which can give us less of heat transfer. But advantage of foam glass is it can really take a lot of load, and you can put it on the floor. Then you have aerated concrete blocks or autoclave aerated concrete blocks, AAC. You have a polyurethane, whether it's a closed cell or open cell. You have expanded polystyrene and you have extruded polystyrene. All of these are generally in a sheet form. You also can get a masonry units of AAC blocks, but otherwise most of them are in a sheet form. And when they are in sheet form, you also need to manage their construction. That means something which is, especially in India, when you have a masonry units, and how do you attach these masonry units with the sheets, and what will the layering of that becomes important. Okay? So if you have about 20 centimeter of brick, you will get about 10 centimeters of cellulose, about 7.5 centimeters with the XPS, 9 centimeters with the foam glass, 6 centimeters with the PU, 8 centimeters with the EPS, and 1 centimeter with the vacuum fiber. Now, vacuum fiber is actually, to me, it's not really building product. It has come from some other industry. But still, if you really need to attain certain kind of heat rejection or insulation, you can use this. So that's the comparative thicknesses. Now, why am I talking about this is, you can achieve same kind of insulating effect by making a thick walls as well, right? But in an area where your land price is very high, your super built up to carpet ratio needs to be in certain range. You cannot afford your floor area to go in a thicker walls. And still, if you need to insulate it, you need to go for certain materials which I described. The lesser thickness, it can give you same amount of insulating effect. Again, don't simply take that, the moment you insulate it, you are solving the problem. No. All will depend upon what is the use of your building and how are you going to operate your building. So insulation and thermal mass, both needs to be balanced out. And we'll talk about that when we'll go to thermal comfort lecture day after, or even tomorrow also passive. So the mechanical strength and thermal properties, both needs to be looked at when you pick up an insulation material. Also the fire. Some of the materials do have a higher affinity with the fire, and some do not. So we need to look at them and we need to protect them. And now, where should we put these material? If we start looking at that, let's say you have a hot and sunny climate. When you say hot, that means temperature is higher. Sunny, that means your radiation is also high. Okay? If you have insulation which is outside, so this is outside, this is inside. If you have an insulation outside, what will happen that the temperature gradient, this surface temperature is, let's say, about 45 degree, this will drop drastically, and then your mass will reduce a little bit of that. Versus if you put it internal, obviously from here to here you will not get that reduction in a temperature, but then you will get. So what will happen is that this guy will absorb up to a certain extent, and then only this. So this is where, whether there was a debate, and it still is a debate, that does your best of the best batsman should be on a striker when best of the best baller is attacking, or he should be at non-striker end. And we have seen most of the time people really put the best little behind, so that first somebody takes care of the brunt of the fast bowler and new ball, and then somebody will start getting in the picture. But that doesn't work when it comes to building, because somebody also already gets affected by it, right? So this will depend, I mean, coming back, this will depend what is the use of, what is the operation of your building. And then if you have a distributed, that means this is Kambal and this is raincoat, right? So if you have a high mass, it will take a while to saturate, and then it will transfer the heat inside. But what happens in a warm climate is that, a hot climate, before this gets, let's say, just imagine that heat has started going in and in and in, and by the time outdoor temperature drops, so it will start going out. This is where the mass is important. This is what exactly happens in a Jaisalmer Havelis, where there are so thick walls. In terms of theory, they are insulating walls, right? So heat comes in, they keep absorbing heat, but before it enters, before it goes to before internal surface temperature goes up, outside temperature drops, and it starts going out. Which generally doesn't happen in Delhi in winter, because your mass will start rejecting heat and will reject the heat, and then the internal surface temperature will become so low that for extended period of your Delhi winter, you will feel cool because of that mass. So sometimes mass does help you, sometimes it may work against you. And hence the calculation becomes important. How much should be your thermal conductivity, and how much should be the thickness, and how much should be the mass. When you have a cold climate, what happens is that your outdoor is low, your indoor you want to retain high, and hence you put insulation outside. Internally, this mass will get warmed up first, but this guy will not allow heat to reject out, so it will still be low. Okay, if you put it outside, you do have a chance. If you put it inside, you will have a chance of bit of condensation just outside the insulating layers, because the temperature has suddenly dropped, and there will be something which will attract or which will condense the air until you get a. Versus if you have a distributed, which have high thermal mass, obviously it will take a while for heat to go out. Now when you have a variable outdoors, so this is really, your outside temperature goes up and down. If you have insulation, obviously it will modulate it. But if you have insulation inside, the modulation actually will take place once the outside layer gets saturated, once the heat transfers takes place there, and then onwards insulation will start acting. And as you know, distributed, it'll take a while for it to come in. Now, just imagine that in an air-conditioned building, when you need to retain this inside temperature in a certain range, and if you have a high variation outside and inside, it becomes very, very important that we keep insulation right where we have to combat. Okay? Because you are not going to get a convective current by opening windows. But if it is a mixed mode buildings, what is a mixed mode building? The mixed mode building means that you can operate building by opening a window. Whenever outdoor is favorable, you open windows, you don't use air conditioner. This is one of the definitions. There are three definitions of mixed mode, but one definition is a temporal mixed mode. That means over a period of time, you change. Sometimes it is air conditioned, sometimes it is non-air conditioned. It's like our bedrooms, most of the bedrooms. The entire bedroom gets operated with air conditioner, or many times it does not. Now, when it does not, and when outdoor cool air is coming in, if your wall rejects a lot of heat when your windows are open, when you close it, immediately you don't need to start your air conditioner because your surface temperature would be low for an extended period of time, and then internal loads will start acting. When they go beyond some point, then onwards you start using air conditioner. In that case also, your internal mass will be very, very important, right? How much heat can it reject in the night time so that during the daytime it helps, okay? And we can keep talking about this more and more, but what I'll do for the timing, I'll move a little forward. How do you measure this? How do you measure conductivity? How do you measure U value or specific heat? And there are two ways which you can do it. One is in the field, okay? You go to the field and you have certain kind of non-contact surface temperature measurements, and you try to understand what is the surface temperature outside, what is the surface temperature inside, and try to understand how that wall is behaving or how the roof is behaving. Then you have a heat flux meters or heat flux sensors like that, which needs to get attached with certain kind of reading instrument, and then you can understand how much heat is flowing at what time. What you are doing here is more instantaneous. Right now, what's the surface temperature? But if you need to keep logging it every hour, you need a logger attached with it, okay? There are new techniques where people also start looking at on-site U value measurements. I haven't seen it functioning, and I have seen two sides of various opinion about it. How well does it calculate U value? But there are these ones try to help you understand heat transfer, versus some of these kits straight away gives you U value. So overall thermal heat transfer values. And then more specific, more comparable way is a laboratory. Because if I go to Jaisalmer, and if I have been to Jaisalmer in the May, and if I measure surface temperature, and then if I go to Jaipur in a June, probably my outdoor temperature condition has changed, and so there is no uniformity by which you can take measurements, or you cannot replicate the measurements whenever you want. That's what the advantage of a laboratory equipment, right? You can keep measuring the same thing in the same conditions over and over. An advantage of that is you can compare two samples, you can compare multiple materials, you can rely on a database. Okay, all these materials have been measured in one condition, hence they are comparable. It's like our exam. Everybody takes exam at same point in time with the same question paper, with the same answer. Even if it is open book exam, everybody is being tested at same point in time, and then your mark sheet comes out. That is what the evaluation is, right? It's not that I will take one paper for her and say another paper for her, and quality of questions are different. Not like that, right? So we'll see some of these, in fact all of these. That's one machine or equipment which helps us to understand how you measure a conductivity of insulation. What we do is that insulation goes in here, about 2 feet by 2 feet, could be any thickness up to 8 or 9 inch. And there are two plates. One plate is hot plate, one is cold plate. And then hot plate will start transmitting the heat into the material. The cold plate will start receiving that heat, and some sensors will keep measuring it. So we get to know about thermal conductivity is not as simple as I'm saying, but probably you will understand over a period of time. Second machine also works with a different kind of material. So this one works on the insulating materials, the other one works for the brick, cement, concrete, the steel, and also same material in different forms. So you know the cement powder versus cement paste or mortar. The moment you add a water, the thermal conductivity will change. Versus cement block. So cement is a cement, but then the form of it, the conductivity changes. So this machine helps us to do that kind of testing. And both of them works on a homogeneous material. So if I cut the brick from top to bottom, brick is the same, right? Or if I cut the thermocol or XPS from top to bottom is the same. So it's homogeneous materials. Versus if I have a red trap bond, if I have Adobe, if I have a wattle and dope kind of construction, or if I have something which is non-homogeneous, right? A lot of air cavity, multiple materials inside, and geometry of that material, I mean all 3D printed kind of stuff, you can't really find a conductivity of it. You have to find straight away overall heat transfer values, which is U value, which goes somewhere here where we actually construct a wall, and you'll be able to see one red trap bond testing going on. So we actually construct the wall. We put the wall into a certain condition where one side is a hot side, one is a cold side, and then we try to understand how heat transfer takes place, and then we find a U value of it. Okay? What we talked about is all wall. Now very quickly, on a roof. All those things which works on a wall, it also works on a roof, but one more additional. So roof U value or roof R value is important because R and U value deals with the conduction side. But roof are also getting highly exposed to the radiation. Walls are also getting highly exposed to the radiation, but not as much as roof. Because walls have a directionality, and some part of wall will be under shade, some will not be under shade, and so on. But the roof all the time will receive, during the daytime, will receive the radiation. Hence, the surface property of the roof becomes important. The roof which do not, or the roofs which have ability to reject the infrared component of the solar radiation back into the atmospheres are called cool roof. You might have heard about this word called cool roof. So solar reflectance is a fraction of solar energy that is reflected by roof. We are not, so when I say solar radiation is the entire spectrum. Okay, ultraviolet, VIBGYOR, visible range, near infrared, infrared. So amount of fraction of solar energy which gets emitted back, reflected back in the roof, and then a relative ability of roof surface to radiate, absorb the heat. So during the daytime, it will keep absorbing through conduction and radiation, but when you don't have a sun, the emittance, emissivity of the surface will allow it to put it back into the atmosphere, and that is what we call it a thermal emittance part. And these both works simultaneously at same point in time for the performance of the roof. And two together gives us a unit called solar reflectance index. It is a measure of solar reflectance and emissivity of material that can be used as an indicator how hot they are likely to become when solar radiation is incident on it. So lower the SRI, hotter the material is likely to become. What will happen is that if you have high reflectance and high emittance, the radiation which is falling on the roof will not increase the surface temperature of the roof, and hence through the conduction, if my surface temperature goes up, through the conduction heat will start transferring inside. That will not take place, hence my surface temperature will remain low, and hence my conduction would be low, right? Thermal emittance is a measure of panel's ability or roof's ability to release heat that has been absorbed even through the conduction. And emissivity is the measure of an object's ability to emit infrared energy through IR part back into the atmosphere. So that's how your black body versus fully reflected body kind of, they are more effective primarily because the gas plate, on a gas plate, the flame, and through the conduction, amount of heat transfer takes place on the non-stick pan is much higher in terms of heat transfer, and that's where the black body comes in the picture. SRI also has an impact on urban heat island. So Professor Lal was talking about how the transport and the rejection from the room air conditioner warming up the urban outdoors. Same thing happens when you have a city which keep absorbing the heat during the day, right, because of the surface property of it, but can't release back because all the mass which is receiving the heat during the daytime does not have ability to put, or rather reject, the heat. And that's where the high emissivity material does two things. It does reduce the reflectance of a material, does not allow you to increase the surface temperature, and emittance allows you to reject the heat, whatever you have achieved, whatever you have gained during the day. It helps you to reject that back, and hence the overall urban environment does not get heated up. Versus these guys, they're like heat sink. They keep absorbing the heat all the time, right? So, most important, that surface, and keep this in mind. Please, please, please keep this in mind. Solar reflectance index is a surface property. Even if fully insulated roof does not have a surface property of high SRI, it may not work in the best manner. And when somebody comes to you and say that, okay, I have made a paint which is high SRI, or which has the ability to reject the heat, or it has a higher reflectance, or I have made a tile which has a higher emittance, don't ask this guy that what is the U value of it. There are many architects, many engineers do ask people that, oh, this is a paint, what's the U value of it? No, U value will work for the conductivity of it when the conduction comes in the picture, right? We are dealing with the radiation, and hence the high SRI paint, you should look at SRI value, you should not look at the U value of it. And hence it's a surface property, okay? However thick or thin your sheet could be, but if it is with the high SRI paint, at least it will work. The reflectance and emittance of that will work for you. Okay, so keep this in mind. SRI is a surface property. Okay. Yeah, so that's you have various kind of paints, you have various kind of coatings, you have various kind of tile available, which has high reflectance and high emittance values, and then combination of this gives you SRI. One more thing, sometimes you may get a SRI which is more than 100, and you always wonder that how can it emit more than what it receives, or emit more than what it reflects. So just don't get confused, because in the past, when somebody derived the SRI, or when they derived the SRI value, they made a sample, and they made a reference sample whose SRI was 100. Now advancement of technology has given us a highly reflecting surface or highly emitting surface which has more emittance value than the base case. Hence we get a SRI which is higher than 100. That does not mean that it reflects more than what it absorbs. But it's like if you make me as a benchmark for mathematics, and if you give me 100 marks, he will get 105 marks, and he will get 136 marks. Because the base which you have created is, at that time was the best, but right now it is not the best. Their advancement has come, and people are doing better than that base case. So when you come across any product with the claim that SRI is 103, 104, don't get confused. Okay, it is that 104 is against the base case of 100. Again, how do we really measure SRI? So there are spectrophotometers and Fourier transform infrared machines which helps us to understand the surface property. Unlike these guys, where the heat has to transfer between one surface to other surface, and we measure a conductivity of how much heat gets transferred from one place to other place, is not the case here. We just need to look at the surface. Okay, whether it's a paint or a coating applied on a plywood or applied on a steel or applied on a brick can have a same SRI, because SRI is a surface property, nothing to do with the conductivity of material. Okay, so what we do is we measure that fresh SRI paint, and most of the code, ECBC and Grihar and IGBC, does talk about SRI values. This is SRI values. It's we call it a virgin or first time measured SRI values. But as you know, that roof will get impacted by dust, salt, pollution, and it will degrade. Right? So there are other tests which we are still developing the methodology and things that are how does it degrade. And we do accelerated testing. What happens in the real world over a period of 3 years, we try to do that very quickly to understand whether this paint will remain like this or it will degrade 10%, 5%, 30% over a period of 6 months, 8 months, 9 months, 2 years, 3 years. And then you decide the performance of that. Okay? So the aging of a roof depends upon the surface, where it is. Probably in Delhi, something will age in 3 months versus in places like Ahmedabad, same material might take about 2 years to age, because difference in a dust deposition, different in a dust, the pollution and so on and so forth, right? So I saved 5 minutes, Sashwati. I started 15 minutes late. I finished 5 minutes before the scheduled time. Anyway, any question?
SRI, the reflectance that SRI talks about is reflectance of the radiative area.
Solar reflectance.
Yeah, that is the radiation. There are 3 types of radiation reflecting the radiation.
Okay. Just go ahead. I mean, I'm a little confused, but you go ahead. Just finish.
And the insulated materials that you're talking about, the fiberglass and all of that, that is stopping the conductivity.
That's correct. That's correct.
So apart from high SRI materials, is there any other way to stop radiative heat? Because insulated materials don't stop radiative heat.
Right.
So how do you stop radiative heat?
High SRI paint.
That's it.
Yeah. That's it. It's too much. I mean, that's it. It's very simple, right? If you have 5 choices, it's difficult to which one should I pick. But if you know this SRI is going to work, you go for better SRI. Easier. Yeah. But the shading, something has to get exposed. Is it? Yeah. Yeah, so what Samir is saying, that there people do take these primary and secondary approach. My primary roof, outer skin and inner skin, right? So my something which is, I mean, obviously to protect this, I have this, and protect this, I have this, right? So if your roof, if you want to protect your concrete roof, you are putting insulation, but you don't want to put a solar reflectant paint because people are going to walk on it and it might get spoiled. You may create one more secondary roof. But secondary roof also will get heated up at one point in time, right? You can't have third roof on top of it. You know that joke where somebody asked that, no, every time what you do at the Indian Railways, they are pretty bewkoof people. Whenever there is an accident, first 2 bogies gets crashed. They should find those 2 bogies has to be at back. Somebody would be at front at least. And so something will take a solar radiation, even if you go for secondary, primary options. Yes.
Okay, so I just wanted to add that what Rajan has covered is the modes of heat transfer. In the afternoon, we are going to use 2 exercises, which practically will then get a chance to calculate first the new value of the quantity, and second a simple problem in which all the 3 modes of heat transfer are taking place: conduction, convection, and radiation in individual cases. And you will have to do a simple hand calculation. So you will get a theme for numbers. What is happening and what are the formulas we are using. So currently those formulas are not being covered. So on 4 o'clock around we will have 2 hours.
So SRI increases the UHI effect or?
So higher SRI reduces the urban heat island effect. So that means that amount of radiation which you are receiving on the total mass, 2 things happening. You are reflecting right away, and high emittance also helps you to reject whatever are you gaining. So it reduces the heat island effect. Do you know what is heat island effect? Okay. Yes. It's related to that, or it's okay.
When it is rejecting as long wave radiation or short wave?
Long wave.
So then it's more adding up to the difference.
No. You're rejecting back, right? So it's, sorry? Back to the sky.
But inside the distribution.
Inside the atmosphere, right? But as we know that 4% of India's land mass is urban space, so then that is a huge heat sink. And in fact, there are some paints who also reject in outer space. Not in building application, but refrigeration. There are paints which rejects the radiation directly into outer space, so not even atmosphere. Right? So heat island is yeah. So I'm just trying to find a parallel, but anyway, in a country, let's say you are talking about, where are you from? Bhopal. Okay. So let's say you talk about the large region, about, let's say, Bhopal would be what, 100 square kilometer? Yeah, 100 square kilometers, let's say Bhopal. You talk about 500 square kilometer around Bhopal. If you look at the thermography image, this would be a warmer spot as compared to 500 square kilometer, right? Why it is warmer? Because amount of solar radiation falling on that space gets absorbed. So radiation falls, and then through the conduction, all that brick and concrete and road mass and pavement and everybody absorbs heat, which does not take place in a farmland. They receive and they reject. No one is there to absorb. Okay. Bhopal buildings keeps absorbing heat. So let's say it absorbs 100%, it rejects 95%. So 5% remains with them. Next day again 100%, 95 goes back. So cumulatively, it keeps everything, entire that mass is warm mass. And that's what we call it a heat island. Okay. So if you are using air conditioner in a farmland, that air conditioner has to give you from 40 degree to 27 degree. Here, that guy has to give you 43 degree to 27 degree. So that has an impact on energy as well. Right?